Okay, thanks, Aaron. So I wanted to start by first talking about the various reasons why a load test may be conducted. I'll briefly review the ACI load testing requirements and discuss challenges associated with conducting a load test. I'll also then review case studies for 3 projects that I was involved with. The load testing is typically performed when the safety or performance of the structure is in question. A building department official or an engineer may have concerns regarding the capacity of a structure. There may be suspected construction deficiencies that may be difficult to resolve using other analysis or additional testing or non-destructive testing techniques. There may also be concerns regarding observed cracking or deflection that's observed. And also load tests are sometimes considered to confirm the effectiveness of unique repairs or retrofits that the building officials or other involved parties may not have experience with. So the load testing requirements are outlined in ACI 437.2 and ACI 318, Chapter 27. The test that I'm going to talk about today as part of the case studies, the applicable building code was ACI 318, so I'm going to focus on their provisions for the 24-hour monotonic load test. The load intensity per ACI 318, the equations are noted here on the slide. When you go to start your loading, first you obtain the initial values of the deflection, and then you apply loads in not less than 4 approximately equal load increments. You measure the deflections after each load increment is applied, and then you test, your test load remains in place for 24 hours, and again, for the monotonic load test. At that point, you take an additional set of deflection measurements, and then you start your rebound, or your unload, I'm sorry, of your structure. Provide 24 hours for the structure to rebound or recover from its loaded position. Throughout that process, you're doing inspections to monitor the condition of the structure. Here are the acceptance criteria. Again, the portion of the structure tested shall show no evidence of failure. The primary criteria is the recovery being less than 25% of the maximum measured deflection obtained during the test at full load. You can also repeat the test, and there's a slightly different recovery criteria if you repeat the test 72 hours later. And the recovery or rebound requirement is waived if the minimum deflection is less than the values indicated here. The purpose of that is to avoid penalizing a stiff structure during the performance of the test. If you have a very stiff structure, the measured deflections may be close to the accuracy of your ability to measure those deflections, so they switch to the minimum deflection requirements here. And you do not have to satisfy the rebound requirements in that case. The load test requirements seem pretty straightforward, but there are a number of questions that must be answered before you get into it. First of all, the parties need to agree on a test area that is representative and how many tests will be conducted. This includes considering the continuous action of the members and potential load sharing to adjacent elements. You also have to think about how the test load will be applied, what you're going to use to apply the test load, and then also how are you going to protect the building and occupants of the building or structure during the course of the test. That involves shoring, typically, that we'll talk about further later, and you need to consider how that shoring is going to be installed. In many cases, the shoring itself can be a significant portion of the load test. And then also, you want to consider what other information about the structure are you interested in obtaining in addition to the deflection measurements. Apply the load. There's various ways. First one I'll talk about is hydraulics. You can use hydraulic rams to react against the floor level above. You can also install through bolts to the slab or foundation below and then pull the structure down. We often use dead weights in our tests and hydraulics, but when you're looking at dead weights, primarily we're looking at either water or other materials such as steel plates or lead ingots. If you're using water, you'll have multiple options for containers of various sizes, or also constructing water tanks custom for the project. If you're looking at just other materials in addition to steel plates or lead ingots, you could also consider using other materials that may be readily available on site. For hydraulics, one of the main advantages is the load will drop off immediately if you have an unexpected failure, which is a big advantage. So that also will reduce the amount of shoring that you'll need, or the size of your shoring. Primarily, your shoring will only need to support the dead load only. You can also apply the load very quickly using hydraulics, which is a significant advantage. Typically, we have a subcontractor assisting us with all of these tests, and you have a large number of laborers on site. So anytime that you can reduce the time associated with loading or unloading the structure, you can save a lot of cost. Some of the disadvantages are, again, with hydraulics, generally a fairly involved setup. They have shoring towers and hydraulic rams and loading cells, and it's just a more difficult setup. Again, the rams require a reaction to apply the load, and you need plenty of point loads to assume uniform loading. Here's just a general photo of hydraulic test in progress. Here we were reacting against a beam above to apply the load to the beam below. You can see the shoring towers and beams in place and the hydraulic rams near the top of this member. The rams, again, spaced to replicate a uniform load. With water, again, you can go with individual containers or large tanks or anywhere in between. One of the key advantages is you start with very lightweight containers. You can bring this material out to the site easily. You can move it very easily before you apply the water or fill up the containers. And you can very easily provide a uniform load in the test area. Some of the key disadvantages, though, are once the water's in place, it's difficult to move it quickly if you have an unexpected failure, which is different than the hydraulic loading techniques. And it could also take a long time to fill all of the containers. You really need to check your water supply and your water pressure in advance so you have a good idea how long it's going to take you to get a large volume of water in. So we'll have the contractor test this, a week out and tell us how many gallons per minute can we supply, so we know how long it's going to take to fill up an area. You also have to drain a large volume at the conclusion of the test in a very controlled manner, and that's important to plan that out ahead of time. And one thing that you might not think about is just protecting against freezing during cold weather. Sometimes we're forced to perform these tests during cold weather months due to various requirements, and freezing the water is a concern to deal with in the past. Here's an overall photo of some large containers. These were 330-gallon totes. These were, again, pre-filled in a different area and moved in using a pallet jack. Here's an overall photo of a large custom water tank that we constructed on a different project. The design of these tanks is very important. I wouldn't just leave it up to the contractor on their own. I would work with them to make sure you have a very stout design. The key is the water tanks can't leak. You need a uniform water level throughout the test. And here you can see there's multiple bulkheads installed to subdivide the areas to address floor slope to make sure that you have a uniform load across your test area. You need to make sure the bulkheads are strong enough to sustain the load and avoid any blowouts during the test, which has happened. And again, you can see, like in this case, this was at an airport parking garage that we were testing. I believe we had 38 inches of water over a very large area, so a very large volume of water that we had to pump out at the end of the test. So we also planned out how much capacity our pumps would have, how many pumps we would need, what drain lines we were sending the water to, all in advance, so we didn't overload their system. Talk about steel plates or lead ingots being used also. One of the advantages is the plates have a fairly small profile, so you can put a large amount of weight in a small area, and you can also use them stacked on top of each other to provide a fairly uniform load or a line load in some cases. Again, the load can't be removed quickly if you have an unexpected failure, and this requires working in the loaded area during the course of the test to move the materials in and out. There's a significant amount of labor required to move the materials. We've done many tests where we're moving over 100,000 pounds of steel plates or lead ingots manually for various reasons, and it can take a very long time to do it, so you need to have a large, motivated crew on site. Here's just a quick photo showing some lead ingots used on a small interior load test where we needed line loads. This is load stage 1 of a line load over, I believe this was a joist floor system that we were looking at, just putting a line load right over the stems. You could see you can use something like this in a small enclosed area where large water tanks or hydraulics may not be a good option. You can also consider other materials, what's available on site. In this case, there was a lot of CMU block on site for other construction that was going on at the building. So the test load was developed using the CMU block. With all of these methods, one thing to point out is you really have to work with the contractor in advance, whether it's water jugs or CMU or steel plates, regarding where they're going to stage the materials and how much you're going to spread it out and what areas you're going to put it in. You want to make sure you're not pre-staging the area or the weights anywhere adjacent to the test areas where removal of those weights could affect your measurements. And you also don't want to unexpectedly overload a test area or an area that you're not testing. Again, you want to install shoring prior to loading, and the shoring should be installed and designed to support both the dead and the test loads in the event of an unexpected failure, unless you're using hydraulics like we talked about before. The shoring should also be installed with adequate clearance to allow for deflections, so you don't want to impact the ability of the structure to deflect during the test. You can tell by this setup, this was just an individual location that we're shoring, but in some cases you're shoring through multiple levels and large areas, so it can be significant expense. Deflections can be monitored in several ways. We typically monitor deflections electronically using cable extension transducers, or CETs, as shown here. A lower tech method is using dial gauges, and it's not as accurate or reliable as the CETs, but it could be used as a good backup method in some cases. A level survey could also be used as a potential backup method depending upon the magnitude of the deflections you're looking at. You can look at considering other instrumentation during the test also. At the center of this photo, this is a beam that we're testing, and you could see an LVDT installed across a crack that we wanted to monitor during the test. I think this is a key component of the testing protocol that we typically put together. You can monitor the cracks visually with crack gauges and making notes and mapping the cracks on the girder, but it's nice to have a direct reading of the crack width during the test without having to go up to the beam, and you can pick up on any changes in real time. On the left side of the bottom of the beam here, you see a small aluminum angle. So our team will install those angles on the underside of the member to be tested. We'll have small aircraft cables that then are hung from those angles, and you drill holes or core holes in the ceiling. Like in this case, the photo was taken in an attic. So those small cables then pass through the holes drilled in the ceiling down to the floor below, which will have the CET installed on it. Strain gauges can also be installed if you're looking at monitoring the strain on the reinforcing steel during the course of the test. And then load cells, of course, are used in a hydraulic setup. Here's a photo of our typical data acquisition system. So you're recording the voltages from the CETs and entering those into the spreadsheet. And we could set this up manually or with an automated data acquisition system that records at discrete intervals or load points. Again, mechanical dial gauges or other survey methods could be used as a backup. This is our primary way of collecting the data. All right, so I wanted to go into our case studies. The first case study was a parking garage in Las Vegas. There were pre-stressed double T-beams on 3 levels, and cracking was observed in the stems of the double Ts about 8 years after construction. The cracks were located approximately 6 to 8 foot from the ends of the double Ts, and the probable cause was related to strand slippage. So there was a different consulting engineer that was initially retained by the owner who recommended that load testing be performed, and they wanted to confirm the capacity of both the typical cracked double T-beams in their current condition and also the capacity of the double T-beams after they were repaired using a proposed FRP repair method in the load testing. So here's a photo of the cracked double Ts. Now that first stem that's closest to you in the photo, that is the widest crack that we observed on the project. Sort of atypical, but it's a good photo to look at here. And you can see the smaller, narrower crack width to the left of that wide crack. Again, these cracks were about 6 to 8 feet from the ends of the double Ts, and they were likely related to strand slippage. The cracks were nearly vertical at the bottom, and then they inclined slightly as they went up the member. So the other consulting engineer developed a repair protocol consisting of epoxy injection and shear strengthening and flexural strengthening using fiber reinforced polymer reinforcement, FRP reinforcement. This photo shows the FRP reinforcement in place at one location, and also the shoring tower that was installed prior to the start of the testing. The load testing was performed in 3 phases. I'm going to focus on the results of phase 1 first. In phase 1, we tested 2 cracked double T-beams prior to repairing them with the FRP, again to evaluate the capacity in the cracked members. And then we also tested 1 double T-beam that had been repaired and strengthened using the FRP to confirm the strength of the proposed repairs. Shoring was installed, as I discussed, below the double T-beams. And we also installed shoring below the spandrel beams that supported the double T's to be tested. There were some concerns, given the cracking that was observed in the double T, that we could have similar issues with the spandrel beams. So to be cautious, we shored the spandrels also. We also cut the existing topping slab and flange-to-flange connections to eliminate load sharing, potential load sharing between the adjacent double T's. We wanted to minimize the area that we required for loading, so we could just load one individual double T without shedding load off to the adjacent T's. And this also minimized the amount of shoring required by just testing that discrete element. We elected to use water tanks to apply uniform test load. Here's just some quick photos of the shoring. On the left is the double T shoring. On the right is the spandrel shoring. Again, the shoring was continued through multiple levels of the garage. We were at least in the first phase, we were testing the roof level of this garage. This is a photo of the crack mapping that we performed prior to the start of the test. So you want it takes a decent amount of time to do this. You want to thoroughly map out all the cracks, record the initial crack locations, lengths, and widths on the member prior to applying any load. We often use a different color to map the cracks during the subsequent load stages, so it's very readily apparent what was the initial crack and what was the propagation of the crack during the testing. Here's a custom water tank that was constructed on the top side. This is, again, the roof level of the garage. That's a tank specifically just over 1 double T-beam. The water tank segmented with multiple bulkheads to account for the slope of the double T's in this area. So we had a uniform test load or water depth and ultimately test load on this double T. You can see all of the cross bracing and some steel cables below the depth of the water level to brace the perimeter of the tank, so it didn't blow out during the course of the test. So the first test, again, was the cracked double T that had not yet been repaired. The specified test load was 65 PSF. We were forced to stop the test when the applied load reached 40 PSF. There was a loud cracking sound, and then the existing crack, or one of the existing cracks, widened from 0.04 to 0.2 inches immediately. So this member failed the load test, and really indicated that the ultimate capacity of the cracked double T beams, at least this beam, was close to the unfactored design live load. The second test was a double T that was tested with the FRP repairs, the shear and flexural strengthening that was installed. At this location, the specified test load was 86 PSF, and no significant additional cracking was observed during the testing. The rebound or recovery was equal to approximately 100% of the maximum deflection obtained during the test. So good results on the second test. Here's a plot of the load versus midspan deflection. You can see very good behavior, a little bit of creep at the 24-hour mark, and then almost 100% recovery here, or rebound. So during the subsequent phases of the project, we tested 11 additional double T-beams after they were strengthened with FRP. Each double T-beam passed the load test with similar results, rebound ranging from 90 to 98% typically. The owner and the engineer and contractor involved continued then with the reinforcement of the remaining double T-beams in the garage, and the building code officials approved the repair method. All right, so the second case study that I wanted to talk about was a test that we did at Perry's Victory and International Peace Memorial in Put-in-Bay, Ohio. This memorial was established to honor those who fought in the Battle of Lake Erie during the War of 1812. It's located on South Bass Island in Put-in-Bay, Ohio. Here's some quick facts. It was constructed between 1912 and 1915, about 352 feet tall. And we were not testing the memorial itself, but the plaza right at the base of the memorial. Here's just a quick location showing the monument. It's located on South Bass Island, and the only access to the island is by ferry. Some photos of the upper plaza during construction, reinforced concrete construction, and again, our work was focused on this plaza at the base of the memorial. There was extensive freeze-thaw damage on the structure due to the long-term exposure to Lake Erie and the winter weather at this location. A load test was recommended at the time to confirm the upper plaza had sufficient capacity to stay open until a repair program was implemented at a later date. We selected a representative area with significant freeze-thaw deterioration. The total test area is about 1,500 square feet, and in that area we were able to test 6 beams, 2 girders, and 2 slab areas. The required superimposed test load was just under 180 PSF, and we elected to use swimming pools installed on the top side of this slab. The contractor that was assisting us with this testing could do that very cost effectively, and it was a simpler method than going with a custom water tank. And water from Lake Erie was used to apply the load. Here's an aerial view from the top of the monument showing the swimming pools that were constructed. This is during the loading. You can see that yellow line leading from the lake to supply the water. And there's a plot of the load versus deflection. So the structure did not fail during the 24-hour hold or initial loading. However, following the removal of the test load, the structure did not rebound sufficiently. The residual deflection exceeded the 25% of the maximum measured deflection, and therefore the structure did not pass this load test. So our recommendations at the time, well, when we were doing the load test, the plaza was closed to the public because they were doing other projects higher up on the actual memorial itself. The short-term requirement was following the completion of that work, we recommended that they shore the plaza area prior to reopening to the public. And then the long-term recommendation was to repair or replace the plaza level structure and install a new buried waterproofing membrane and pavement surface above. So going into the third case study, this was a series of schools that was built in the mid-1920s. This was the first reinforced concrete buildings in this public school system. And the typical structure consisted of one-way reinforced concrete joists spanning between the exterior walls and the interior beams. Shortly after construction was completed, there were alleged design and construction issues related to rebar placement, concrete consolidation, cracking, and some structural design deficiencies. About 5 years after the construction, the roofs were reinforced or shored with structural steel beams and hangers installed on the exterior of the building. The roof membrane and parapets required a lot of maintenance over the years due to the existing reinforcement method. To give you an idea of how much steel was installed, this is the roof level of the building, and you could see steel beams installed in almost every bay. The tie rods extend down through the roof structure to grab or to connect to a second grillage of steel in the attic space to shore up the entire reinforced concrete roof structure at the vast majority of this roof. The secondary grid of steel installed below the roof structure was hanging from those hanger rods. There's a photo of that in the attic space. So here you have double channel sections installed in the attic with screw jacks that come up and grab the or are in tight contact with the underside of the concrete joist. Again, as you might imagine, looking at this detail, the maintenance problems consisted of recurring roof leaks at the hanger rod penetrations. Again, this was installed in the early 1930s, so their waterproofing methods were not nearly as reliable as they are today. They also had a lot of cracking at the parapet walls due to thermal expansion and contraction of the exposed steel beams. The school board retained us to do an investigation and analysis of this building to determine if there were other solutions to minimize or eliminate the maintenance problems. So our analysis found that the existing supplemental steel typically did not address design deficiencies. There were some design deficiencies, but it did not warrant the amount of structural steel that was added for shoring. Our field investigation also didn't we didn't observe any gross deficiencies in the overall concrete construction. There were some issues, but again, there were more isolated conditions that we were addressing. So we recommended that the original concrete joists and girders be reinforced with FRP. We used some other reinforcement methods at selected areas too, but FRP was our primary method. And then we specified that concrete repairs and other items be addressed at isolated locations. And for all the other areas that we weren't addressing, we recommend that load testing be confirmed or be performed to confirm the structure had sufficient capacity before we took the steel beams off the roof. 8 representative areas were selected for testing at this particular school, and the testing was done in 2 phases, once during spring break and once during summer break when the school building was unoccupied during spring and summer break. The applied test load was 55 PSF, and the deflections were monitored electronically using the CETs and LVDTs. One unique thing about this test is we lowered the existing steel shoring so the concrete structure could behave independently. The advantage to the steel shoring beams was that they could also be used as shoring if we had an unexpected failure. So we didn't have to install independent shoring. We just relied on the steel beam grid system after checking its capacity. The joist areas were loaded using water jugs. Here's a photo of some of the laborers moving the jugs into place. We initially considered using water tanks on the roof, and this photo might not do it justice, but there's significant slope on the roof and other constraints that made constructing water tanks very difficult. The jugs were pre-filled prior to the start of the test and moved into the test areas in 4 equal increments. Here's an overall view of one area with the water jugs in place. And these are 6-gallon water jugs, about 52 pounds per jug. For the girder tests, we recreated a line load over the tops of the girders using lead ingots. The typical girder test was about 23 to 25,000 pounds line load over about a 15-foot span for the girders. All of the areas passed the test. The joist areas would typically satisfy both ACI criteria with good rebound, 85 to 90% typically. The girder deflections were very small. These were fairly deep members with fairly short spans, and the typical deflections are about 1/10 of an inch. They typically passed the test under the maximum allowed deflection criteria rather than the rebound deflection. In some cases, they would pass under both. And then following the load testing, the FRP reinforcement and other repairs were installed, and all of the steel shoring on the roof and in the attic space was removed. So the condition at the school was greatly improved, and they could replace the roof membrane and do their parapet repairs and not have to recreate all of that maintenance going forward. Okay, that's all I have for today. Thank you.